Okay, so now that I'm recording, as I was saying, tests will be back on Wednesday. I've graded most of the tests that have been completed. Um, the scores are all over the place. So there's a maximum possible score of 120, because if you get every single problem right, plus the bonus. Nobody did that, but a few people came very, very close. But there's scores that were far, far lower than that. There was still hope because there's a chance to improve. There's a comprehensive final exam. If someone does well at a comprehensive final exam, that's a good indication that they really know their stuff, even if they didn't demonstrate it on this test. What I would like to hear from anybody, any thoughts they might have about how the test was conducted, and that you are given feedback and then a chance to do that again. Does anyone have any comments about any particular, besides the obvious, any particular benefit, or maybe a reason not to do that? Because it's something I want to try to decide if we were to continue doing that going forward.
I really liked it. It seemed to combat a lot of test anxiety that you would normally get by having that one chance.
Yeah. I will say this, that of the top scorers, what I observed was that there are some that did very well the first day, and therefore were just cleaning up after that. And then there's some that, after the first day, if it ended there, would not have gotten a good score, but then recovered nicely. Okay. Any other comments?
I thought it was incredibly fair.
Well, that's good. Okay.
Beyond fair.
Okay. In retrospect, probably should have rethought certain aspects of a first problem. I can see how it might be psychologically damaging if you come out swinging with a really hard one first try. But okay, because what I have in mind, I will do this again certainly for the second test. Similar format. There's room in the schedule to do that. Things become a little more difficult for a final because we have a university scheduled final exam, and that's kind of the do or die time. There's nothing that really nothing that can be done past that point. So what I'm contemplating doing for that is the week before. I have a class period to work with because I figure there'll still be enough time to do some review. Because the final will be comprehensive, but it will focus on anything that's covered since the second test, like the Laplace transforms and such. Is use some class time the week before to kind of give you guys a sneak peek, so you can start your work then. In fact, when I was a student, I had a chemistry professor who gave the hugest problem on the test up front. Gave us some time to think about it and then take the real thing. So, okay. So, because when it's 50 minutes, one freeze up and you're dead. And there's something to be said for being able to perform at that moment, but often, even in real life, you do get a second chance. It's not the kind of thing that I want. I want your grades determined by your knowledge, primarily. Yes?
Since each question is worth 15 points,
yes.
Theoretically, the bonus is worth also 15 points?
Yes.
So then the max score is 1 out of 105. So whatever score we get, is it out of 105 and then
no, it's still out of 100.
Oh.
Yeah. So if you didn't touch the bonus and did everything right, and I think there was someone in that category, they have a more than perfect percentage.
Oh, okay.
Yeah.
So we also get an additional 5-point lenience.
Right.
Okay.
Yeah. Yeah. It all depends on how many problems I put on a test. because I don't like to think, oh, this should be worth 10, this should be worth 15, or make it worth a fraction or something. So because other times, like if I have 14 problems, I make each worth 7 for a total of 98, and then I throw in 2 points for free. So, okay, so that's one item. Homework 5. I made an announcement, but I forgot to update the website about this. I'm going to set the due date as today, therefore it can be turned in by tomorrow morning. So I have 2 assignments. One was slid under my door on the weekend, and one just now, that I saw just now. So if you really feel done with them, great. If not, you're welcome to more time on them. And I will. And if anyone has any questions on them, you can ask now. So these problems were easy peasy. Okay. Of course, you guys have had a fair amount of practice from these problems already. And yeah, I didn't give anything so unusual this time. Okay. But anyway, by tomorrow morning on that one. I haven't forgotten, there's still a problem set 4 stack of O's I have to grade. And I'll get that soon. The test is definitely coming back to you on Wednesday. I will try to have homework 4 also back by then, if not, certainly on Friday. Okay, now, so today we get into another chapter. Chapter 2 is all about first order equations. And now we're going to take it up a notch to second order equations. So equations involving a second derivative. So the general case is equation in this form. Some function f of your independent variable t, which could be x, y is involved, and y prime, and then y double prime is equal to 0. So any second order equation can be written in that form, where f is whatever function you choose. It could be linear, it could be nonlinear. But what I'm going to do today is focus on a very specific kind of equation. This form, y double prime plus some constant p times y prime plus another constant q times y is equal to 0. P and q are constants. Now, the way we can classify this equation is using similar terminology as before. It is a linear equation. It has constant coefficients. So if p and q have been functions of t, it would still be linear, but it'd be a variable coefficient equation. Now, the fact that right-hand side set equals 0, here's an unfortunate use of terminology here. Because of that, we call it homogeneous, which has absolutely nothing to do with the use of homogeneous from last chapter. It's coincidence, using the same word but different context. This actually corresponds more to the use of the term homogeneous that you might have seen in linear algebra. You have a system of linear equations, ax equals b, where your right-hand side b is equal to 0. That's also called a homogeneous system of equations. So it corresponds to that meaning. So we're going to start with this. Much of the chapter will be spent on this. But as we get towards the end, we're going to have something non-zero here, some function like g of t, and that will be an inhomogeneous or non-homogeneous equation. And we'll have techniques for that. Now, because this is a second order equation, we need 2 initial conditions. than 1. So in general, whatever the highest order derivative is in your equation, that's how many initial conditions you'll need. So my usual notation will be y of 0. I could use whatever initial time I wanted, but for now I'll stick with 0. Is some given value y naught. So you're used to that. And then we have initial condition on the derivative at the same time. And I'll call that value z naught. So now we have an initial value problem that has a unique solution. Okay. Now, my goal for today is to actually derive the solution to this kind of problem, at least in most cases. Because how it's normally done, I wasn't really satisfied with. For instance, if you look in the textbook, we're in section 3.1 right now. If you look in the textbook, when they discuss this kind of equation, what they do is they say, let's assume the solution is of a certain form, e to the rt. Plug it in here and figure out what r must be. Now, that is a good way to, that leads to a quick way to solve a problem, and that's something you can do in homeworks or tests, and that is what we will conclude with. But you're left thinking, okay, what made someone think to do that? Why is that a good idea? Just assume a solution in a certain form. What is that assumption based on? Now, if you look in my notes, I don't do that. I fall back on what we know about first order equations. But in the notes, I use a lot of linear algebra. How many of you have not taken Math 326 yet? Or maybe we never will. Yeah. Okay, a lot of you. So I'm not going to do that either. I mean, those of you who've taken it, it's there in the notes if you want to look at it, but I'm going to do it a different way that just uses ordinary algebra. And what we already know about solving first order equations, because any equation of higher order can be written as a system as a system of first order equations. And that part's actually quite easy to do. The rest of the stuff I'm going to show you a bit of pain. So these are new notes, and I will, they're actually posted on the site under the examples page. Okay, so what I'm going to do is rewrite the second order equation as a system of two first order equations. So that's something you can do in general. If I have any number, if I have a 100th order equation, I can write it as 100 first order equations. The way you do that is you introduce new independent variables. So I'm going to let u1 refer to y. So u1 is now what I really want to solve for. And then u2 is used to refer to y prime. So now what I can do is I can figure out two equations, first order, for u1 prime and u2 prime. Now, since u1 is equal to y, u1 prime would be equal to y prime, but what else refers to y prime? u2. So this is my first equation. u1 prime equals u2. Second equation is more interesting. Now, u2 is y prime. Therefore, u2 prime is equal to what? Y double prime. Now, if I go back to my original equation you have on board, that's the same as if I isolate y double prime, that'd be equal to minus qy minus p y prime. But now I can write that in terms of the new variables. So what should this be in terms of a new variable?
Minus Q1.
QU1, yeah. 2, 2. Okay, so now y is out of the picture. Also, there are no second derivatives anymore. So now I have this system. I'll just summarize. U1 prime is equal to U2. U2 prime is equal to minus QU1 minus P U2. Now, first order equations, of course, should have initial conditions. So my initial conditions, U1 of 0 is equal to the initial value for y. Well, that would be y naught. And then U2 of 0, well, U2 is y prime. So I need the initial value for y prime of 0, but that would be z naught. So the initial values from the original problem just carry over. So now we are tasked with solving this. Now it's a system of two first-order equations. Now, what we'd like to do is use this, use what we know about first-order equations, what we spent all this time on all semester long, to solve this. But we can't do that right away. We didn't learn about solving a system of equations. We would just have a single equation, and we could, and these are linear, just like we've seen before, except for one thing. These equations will make them difficult. They are coupled together. So equation for U1 prime depends on U2. Equation for U2 prime depends on both variables. What we need to do is try to find a way to separate them. If we have two first-order equations that are independent of one another, well, then you can fall back on what you know to solve that. So we want to try to pull these equations apart. So we make another change of variable. So I'm going to express U1 as a linear combination of two new variables, W1 and W2. And the coefficients, Pij, those will be constants. And then U2 is also a linear combination of these same new variables. Okay. So the idea is we want to come up with equations for W1 prime and W2 prime that only involve W's. We want to get U's out of a picture in such a way that the two equations are independent. So now what I can do is I could take these formulas for U1 and U2 and substitute them in there throughout. And it's going to be a big mess, but it'll lead to a way to solve these. They're saying that mathematics is the art of reducing all problems to linear algebra. And it's kind of what I'm doing, but I'm trying to avoid using like matrix vector notation since not all you're familiar with that. So in the end, we're just boiling down to ordinary algebra with a touch of simple first-order equations at the end. Okay. Now, here's where things begin to get ugly. So if I take those expressions that I just wrote for U1 and U2 and plug them into my system of first-order equations, I have P11 W1 prime plus P12 W2 prime. So this is U1 prime. Now, the derivative of U1, that just carries over to the derivatives of W1 and W2 because the P's are all constant. So that part works out nicely. And then on the right side, I have my expression for U2. So P21 W1 plus P22 W2. Okay, and then for second equation, I have U2 prime. And then I'm going to have minus Q times U1 minus P U2.
Are those primes W1 prime?
Over here, yes. And for now, we won't bother with the initial conditions. We'll deal with that at the end, if there's still time. Okay. Now our goal is to isolate W1 prime and W2 prime. So we want equations W1 prime is equal to something that involves only W1, W2, and then the same thing for W2 prime. So what I'm going to do is you can actually approach this just like you would solve any other linear equation. It's the same manipulations, just with different entities than what you're used to. So I'll first start with this equation, first one, and I'm going to isolate W1 prime. Now, so that means I need to take that and move it to the other side. So I'll have what was already there. P12W2 prime. And then I'll divide all of that by the coefficient of W1 prime. So that's P11. And now I'm going to take this and substitute it into the other equation. So these are things you do from solving any system of linear equations. Working on the elimination stage, and then later I'll do some substitution. Now, once I substitute that in there, things get even uglier. And it's probably a good thing I just written out in advance. So I have P21, and then I have this denominator P11, and then I have all this mess in the numerator. Okay, and then I still have, well, the rest of this equation stays the same. W2 prime. That's a 2. A little bit of it got smudged out. Okay. Equals, and then the right-hand side doesn't change at all. Yet. Okay. So now here's where we're at. I try to avoid heavy denominators. They just complicate matters. So what you can always do is just write out or multiply through by P11. So now I have, and also I can take this P21 and I can multiply through. So I have P21 squared W1 plus P21 P22 W2 minus P12 P21 W2 prime plus, so now I multiply through by P11, so everything else is going to have an extra factor of P11 added to it. Okay, so that's just the left side, and then everything on the right side I need to multiply through by P11. Now things are getting a little bit out of control. What's my goal here? My goal here is, because W1, you don't see W1 prime anywhere in this equation. We already eliminated it. What we want to do now is we have W2 prime in here, so we isolate W2 prime. And there are two terms here containing W2 prime. So we're going to leave those on the left side. We'll factor W2 prime out. And then everything else is going to go on the right side. Okay. But, all right, so I'm going to isolate W2 prime on the left. And then on the right side, all I'm going to have, every term on the right side is going to have a W1 or a W2. So what I want to do is group by W1 and W2. In other words, I want to gather all the W1 terms together in one place and then gather all the W2 terms together too. So that's what's going to happen in this next step. And believe it or not, simplification is just around the corner. All right. Now, okay. So W2 prime, then I'm going to have a big long numerator. If you look at what was multiplying W2 prime, what do we have? P11, P22 minus P12, P21. So I'll go ahead and, so that gets factored out, and then it's going to divide by it. So that's what's going to appear in the denominator. Okay, so P11, P22 minus P12, P21. Does anyone recognize what that is from some other class? Like if I make a matrix and I put all the P's in it, arranged like that. What? Yes, it's the determinant of, this is a matrix for the change of variables. So of course we need this to be non-zero. In other words, my change of variables from U's to W's, it has to be invertible. So that's something that we'll have to come back and deal with later. Okay. Now, everything else, what I have is, we end up with a minus, because we have something times W1 plus something times W2, but all the terms end up having minus signs in front of them, so I just pull the minus out. So we have P21 squared plus P11, P21 plus Q, P11 squared. So those are all the terms on the upper board that are multiplying W1. I just factor W1 out. And I need the same thing with W2. You have a bunch of terms multiplying it. So I have P21, P22 plus Q, P11, P12 plus P, P11, P22. Okay. Now, I can finally give you an idea as to why I'm going through all this madness. Because I want equations with W1 and W2 prime that are independent of one another. So I want this. I want that to be 0. If I can make that 0, because the P, I, J, I haven't chosen them yet. If I can choose them in such a way that that whole term is 0, then I have W2 prime is equal to something times W2, and that's it. So, and that's an equation you know how to solve. So if I look at this equation, P21 squared plus P11, P21 plus Q, P11 squared, I need that to be 0. Now, the written down form doesn't really help me, so here's what I'm going to do. I'm going to assume, I need either P11 or P21, those are the only P's I have in here. I need at least one of them to be non-zero. Because otherwise, if they were both 0, this would be 0. So I'm going to make an assumption here. Assume P11 is non-zero. That way I can divide by it. In fact, I'm going to divide by P11 squared. So I get P21 over P11 squared plus P. Recognize similar manipulations from homogeneous equations. plus q is equal to 0. Or what I could do is I can notice I have p21 over p11. That's being squared. The same expression over here. So I'm just going to name that something. I'm going to call it lambda 1. Lambda 1 squared plus p lambda 1 plus q is equal to 0. Where lambda 1 is defined to be p21 over p11. So now I have a quadratic equation. So I just need lambda 1 to be root of this, because p and q, those are given. Those come with the original problem.
It's a 0, so.
What?
Is that a 0, so?
Here, yeah, 0, comma. Okay. So, and the thing is, when you solve these kind of problems for homework, you're not going to go through all this. You're going to get to jump directly to here. What I'm doing now is explaining why that actually works. Okay. Now, so this condition must be satisfied. Doesn't tell me what P11 is or P21 individually, but it does tell me what their ratio is. So I'm going to make a choice. I'm just going to let P11 be equal to 1. The simplest possible choice. And then P21 is equal to lambda 1. Where lambda 1 is a root of, and this is an important term for you guys, of the characteristic equation. So that's how all textbooks tend to refer to this. Lambda squared plus p lambda plus q is equal to 0. So this will become very important to you when working any of these kind of problems. But in the textbook, we tend to use an R. I like lambda because this corresponds to an eigenvalue from linear algebra. But doesn't matter. Point is, you need the roots of this. Okay. So if your p's are chosen that way, then the equation for W2 is now separated from the equation for W1. Now, so now we can make this 0. But if we do that, what about this? If we're going to solve this equation for W2 now, we still need to know what coefficient's in front of it. So here's something that's a good to know thing that they really should teach everybody about roots of quadratic equations, but no one ever seems to do that. So I'm going to tell you now. If I let lambda 1 and lambda 2 be the two roots of this equation, so you go ahead and do your quadratic formula, plus or minus, and you get to two roots. Then here's some good to know things about these roots. First of all, their sum is always equal to minus p. Also, their product is equal to q. Now, you learned this back when you learned factoring, but then it seems to be forgotten. But it's useful in so many other situations besides just factoring. In fact, any polynomial equation, if a leading coefficient is 1, then the product of the roots is always the last coefficient. And then the sum of the roots, negated, is always the second coefficient. In the case of a quadratic, that just happens to determine everything. So now I can take advantage of these to figure out what that would be. And I get my equation for W2 prime. Okay, so once I take advantage of what I know about lambda 1, lambda 2, and p and q up here, then this equation is about to get a whole lot simpler. So now I have W2 prime is equal to, and I have minus up front, W2 is factored out. The denominator reduces to this, P22 minus lambda 1, P12. because I'm using P11 equals 1, P21 equals lambda 1 throughout. And then the numerator reduces to lambda 1 P22 plus Q P12, because P12, P22, I don't know those yet, plus P P22. But now, when I take advantage of what I just wrote over there, that how P and Q relate to everything, I end up with just W prime is equal to lambda 2 W2. So this simplifies to this using these relationships. All right. So you can try it yourself. So this is one of these things that it is safe to try at home, fairly. Okay, so now we have an equation we know how to solve. Now, if I were to go back, far back, to where we had the two equations, and do similar but opposite manipulations, if I wanted to isolate W1 prime, I would get the same kind of thing. Where lambda 1, lambda 2 both satisfy this characteristic equation. Lambda squared plus P lambda plus Q is equal to 0. However, there's a limitation. I need this determinant, P11, P22 minus P21, P12, P21. Now, P11, I said earlier, is equal to 1. P22, that will equal lambda 2. P12, I also said equal to 1. And then P21 is lambda 1. So this just reduces to lambda 2 minus lambda 1. Must be non-zero, because I had that in the denominator. So in other words, this only applies if roots are distinct. Now you can use it whether the roots are real or complex. For now, we'll assume they're real. When they are complex, we're going to look for a solution in a different form. So everything I've just done here doesn't work if this quadratic equation has a double root. And that's something we'll deal with later in the chapter, so we won't worry about that now. Okay. So these equations, you know how to solve. Lambda 1 and lambda 2 are constants. So can anyone tell me what the solution to this looks like? You've done it before. E to the what? Lambda 1t times whatever its initial value is. And then similar for W2t. Okay. So now we can write down our solution, the form of our solution. So y of t, the solution of our original problem, y is equal to u1. But u1 is expressed as a linear combination of w's. That's p11 w1 plus p12 w2. But both of these, p11, p12, it was decided earlier that those would be equal to 1. So it's just w1 plus w2, and now we know what those are. So w1 of 0, e to the lambda 1t, plus w2 of 0, e to the lambda 2t. Now w1 of 0 and w2 of 0, those are constants. And we're not preoccupying ourselves with the initial conditions for now. So general solution is y of t is equal to some constant, e to the lambda 1t, plus some other constant, e to the lambda 2t, provided that lambda 1 is not equal to lambda 2, where lambda 1 and lambda 2 come from this. So these two things right here, that's what you'll actually do on a homework problem or a test problem. You'll be given the original equation for y double prime plus py prime plus qy equals 0. You'll solve this characteristic equation for the two roots, lambda 1, lambda 2. They'll be distinct. If the roots are distinct and if they are real, you can just jump directly to this, and you're done. If there's an initial condition, then you can use that to solve for. So let me summarize in a nice, neat way for your notes. Okay. And then I can take into account additional conditions. So on y and y prime is so what lambda 2 are distinct real roots of this equation. Lambda squared plus p lambda plus q is equal to 0. And this is your characteristic equation. Okay. And if you are given initial conditions, you solve this system of equations. It comes from the fact that u1, which is y, is p11 w1 plus p12 w2, and u2, which is y prime, is p21 w1 plus p22 w2, and this holds at all time. So it certainly holds at t equals 0. So we get w1, no, sorry, c1 plus c2 is equal to y naught, and then lambda 1 c1 plus lambda 2 c2 is equal to z naught. And all it did was, using the fact that p11 and p12 are equal to 1, p21 is lambda 1, p22 is lambda 2. These were arrived at earlier. Also, C1 is the initial value of W1. C2 is the initial value of W2. So that is how I got from this system of equations that comes from my predefined change of variable to this system that you would actually solve. So just for 2 minutes catering to the whole, or caving to the whole teach to the test thing, the way you would solve this problem on the homework or test is do that first, do that second, and then if there are initial conditions, you solve this last. And then you can fill in the values of C1 and C2 up here. Now, if the roots are complex, this technically still works, but then we would have complex numbers in a solution when the actual solution to this equation is real, even if the roots are complex. So we would rewrite it to get it into a real form. So only the case of repeated roots is not dealt with yet. In that case, it's actually not possible to separate the equations for W1, W2 completely, but you can separate one of them, solve it, and then use it to solve the other one. So we'll deal with that another time. Okay. Questions or are brains all fried? Okay. Well, I'll give my last thoughts to this to start a class on Wednesday. We'll continue with this. Okay.